Today, we're going to be talking about positive feedback op-amp circuits. And I'm going to talk a little bit about what feedback networks and things like that entail first. So let's call this positive feedback op-amp circuits. And then the first thing that I'm going to talk about today is a very basic introduction to feedback systems. And I'm going to introduce feedback systems by using a signal flow diagram like we used on the second day of class. Okay. So I'm going to start with a block here in the middle. And that is going to represent my open loop amplifier system. Okay. And my open loop amplifier system is going to have a gain of AOL. I'm not saying specifically that this is a voltage amplifier or current amplifier or anything like that. It could be anything. We're dealing with everything very generically right now. So I've just got this open loop amplifier system. And we know that in an open loop system over here to the right-hand side should be our output signal, which I'm just going to call Y. And I'm going to make a note here. This is our output. And then over here on the left-hand side, we would have our input signal, which I'm going to label as X sub I. So that is the open loop amplifier signal flow diagram like we've been dealing with in this class thus far. Okay. So what we're going to do today is we are going to be applying some feedback, okay? So below this open loop amplifier block, I'm going to put a new block, and this is going to be my feedback network. Like so. And essentially what I'm going to do in a feedback network is I'm going to take some portion of my output signal and I am going to feed it into my feedback network like this. So essentially what I've got here is my amplifier output, and then that same signal is essentially serving as my feedback input. And then this feedback network is going to have a characteristic parameter K, which is telling me effectively the amount of feedback. That's going to be different for different types of systems. Most op-amp circuits that we're dealing with, it's going to wind up being a ratio of resistances and things like that. But when you get into your control theory classes and all of that kind of good stuff, it could be some combination of resistance, capacitance, and inductance. I'm leaving things very generic right now and just saying it's some sort of feedback network that has a feedback factor of K. The output of our feedback network down here is actually then going to be applied to our input. So I'm going to make a slight modification on the input side here, and I'm going to add a summing block, okay? So essentially, we've got this summer, and I can either be adding that feedback output signal or I can be subtracting it. And the value of, or so the sign on that, the plus or the minus is going to correspond to either positive feedback with a plus sign or negative feedback with a minus sign generically. And over here on the far left-hand side is where I'm going to have my kind of true input signal that I'm going to call X sub S. Let me label a couple of things here really quickly. So this portion right here is my feedback output. This portion right here is my amplifier input. And that amplifier input is different than the input signal that we are applying to the system as a whole. Okay. So X sub S is the input that we are applying to the system as a whole. Y is the output we're taking for the system as a whole. And we're going to try to sort out what the relationship between all of these things are. Okay. So let's start by looking over here on the output side of things. And I know it might seem like a little bit of a weird place to start, but it'll make sense here in a moment. Okay. So our output signal Y, sorry, let me do this in black, is going to be AOL times my amplifier input signal X sub I. Okay. So that's literally just this symbol or this signal right here, X sub I, whatever that happens to be, gets fed through my open loop amplifier. So this is what's called our forward path and generates that output signal Y. Now we are going to take our output signal, apply it to our feedback network. And so this is going to give us essentially a feedback signal, X sub F, that is going to go into that summing block. Okay. So X sub F is just K times Y, because if we have a signal of Y going into the input, the feedback network is going to act on that input and it's going to generate a feedback signal of K times Y. And then now let's see what's going on with this summing block. Okay, so I have a signal XS that is one of the inputs for the summing block. I have a signal XF that is the other input for the summing block. So I can say that X sub I is going to be equal to XS plus or minus XF, my feedback signal. Okay. So that's my signal flow diagram. And for what it's worth, this path through the feedback network is commonly referred to as the feedback path. Okay. So essentially, what we have in any generic feedback system are four essential parts. Okay. Our first essential part is what's called the feed forward system. So the feed forward system is an amplifier that is characterized by its open loop gain AOL. This system amplifies its input signal x sub I by a scaling factor of AOL generating an output signal of y is equal to AOL times x sub I. So this amplifier block right here is essentially, the feed forward system. The next important part of our feedback system is going to be a sense mechanism. So the sense mechanism is simply a system or network that measures the output signal. So in a real practical feedback network dealing with an op amp, this is usually just simply the load resistance effectively. So this node right here is going to represent our sense mechanism. So this is where we're taking our output or where we're measuring our output at. Okay. The third part of our feedback system is the feedback network itself. So our feedback network is a network of components characterized by its feedback factor, K. The feedback network senses the output signal Y and generates a feedback signal X sub F is equal to K times Y to the return mechanism. Sorry. And then our last important part is the return mechanism itself. Well, let me label this guy though. So our feedback network, I mean, it's already literally has that title, but I'll put it here. Is this guy. And then, sorry, we have our return mechanism. So our return mechanism is a system or network that combines the feedback signal XF and the source signal XS to generate the input signal, x sub I is equal to xs plus or minus xf where the sign plus or minus of the combination determines the type of feedback system. Okay. So let me just put a label on this guy right here. So this is our return mechanism. And in an op-amp circuit, this return mechanism is usually related to the differential input of the op-amp itself. So the op-amp, the fact that it has two inputs, a non-inverting input and an inverting input, is actually what is used to serve the role of that return mechanism in these circuits. So still keeping things kind of generic, what I want to do is use this signal flow diagram to develop a relationship for what we're going to call the closed loop gain, or the feedback gain of this system. So instead of having just an open loop gain, we are now going to have a new gain that is characteristic of the system as a whole, including the effects of that feedback network. Okay. So we're going to start today by talking about a positive feedback system where the sign on that summing block right there is a plus sign. Okay. So let me just put a note down here. So for a positive feedback system, so we can see pretty easily that y is still going to be equal to AOL times x sub I, right? So I'm going to write that down first. Well, in a positive feedback system, x sub I is going to be xs plus xf. So those two guys are going to, those two signals are going to add together. So that'll give us AOL times XS plus XF. And we know that XF, our feedback signal, is actually just K times Y. So I'm going to substitute that in as well. So we would have AOL times XS plus K times Y. And I'm going to now just kind of expand this thing out a bit, okay? So I've made several substitutions. So what I'm going to have is Y is equal to AOL times XS plus AOL times K times Y. I can move that AOL times K times Y to the left-hand side, which is going to give me Y minus AOL times K times Y is equal to AOL times XS I can factor out y from the left-hand side. So that's going to give me y multiplied by 1 minus AOL times k is equal to AOL times XS. And now what I'm going to do is I'm going to define my closed loop gain, ACL, is going to be equal to my output signal Y divided by my input signal X sub S. And so what I'm going to wind up getting here when I do this math is simply AOL divided by 1 minus AOL times K. So this is my closed loop gain for my positive feedback system. So we are going to make an assumption here. We are going to assume that our feedback factor K is always going to be positive. So if we're trying to implement a positive feedback system, then we need K to be a positive quantity. Otherwise, we accidentally have negative feedback, okay? So what can I say about my closed loop gain as compared to my open loop gain? Anybody have any thoughts?
Yeah, so
I mean, we can always express things as a percentage. I'm looking for something a little bit more concrete than that. So I have an open loop gain, and then I'm dividing it by a factor of 1 minus something. So if AOL times K is a quantity that is smaller in magnitude than 1, then my closed loop gain will always be greater than my open loop gain. Okay, so I'm going to make a note of that real quick. So ACL is greater than AOL when AOL times K is less than 1. That K looks shitty. Okay. So essentially, in a positive feedback system, we should expect to see that our closed loop gain is larger than our open loop gain. Now, what do you guys think might be a consequence of this? So in the context of the circuits that we've been talking about, where we have a very large open loop gain, if our closed loop gain is even larger, that means that our linear range of amplification is going to be even smaller. So whenever we have a positive feedback op-amp circuit, we know definitively the output of that system is always going to be in saturation. We are either going to be at VCC plus, or we are going to be at VCC minus, because the linear range of the system is so incredibly small, it practically does not exist, okay? So earlier for the open loop systems, we were talking about a linear range of, you know, plus or minus 50 to 100 microvolts. We're talking about potentially nanovolts or less of linear range on a system like this. So for all intents and purposes, we either swing from VCC minus to VCC high or the other way around. There is no linear amplification. Can you guys think of a situation where you might have experienced positive feedback before? So without realizing it, I would be willing to bet that most of you have experienced positive feedback in your, not necessarily everyday lives, but at times throughout your life. How many of you have ever been to a presentation or a concert or anything like that, and you've heard feedback out of the loudspeakers? That is exactly what is going on here, okay? So let me put that into context. The input in that particular system is the sound or pressure wave that is being picked up by the microphone itself. That is being fed into the PA system or the public amplification system and is being output through some speakers. Well, if the microphone picks up the sound that is being generated by the speakers, we have a feedback system. Those two signals add together over and over and over again until we start hearing that high-pitched squealing noise that we call audio feedback. That is 100% a positive feedback system because the signal that's being picked up from the microphone, our voice, is being added to the signal that's being picked up by the speakers. They're combining together, and the amplitude of that system is getting larger and larger and larger, which is generating that sound. That is positive feedback in our everyday lives, okay? So a lot of times, but not all of the time, positive feedback is a negative thing, okay? We're going to talk a little bit about why it might be considered a negative thing here real quick before we get into some useful applications of it. So one of the biggest reasons why positive feedback systems are used so infrequently is what's called gain sensitivity, okay? So essentially, gain sensitivity means that a small change in the open loop gain causes a large change in the closed loop gain of the system. So let's look at a simple example of this, okay? So let's say that I have an open loop gain of 10 and a feedback factor K of 0.0999, okay? I am not going to round that up to 0.1, and we'll talk about why in just a second. So for a system characterized by these two things, an open loop gain of 10 and a feedback factor of K is equal to 0.0999, our closed loop gain, ACL, would be, just to remind you, that's going to be AOL over 1 minus AOL times K. So that's going to be 10 over 1 minus 10 times 0.0999. Somebody throw this into your calculator for me and tell me what you get. $10,000. So 10 to the 4. So as we expected, our closed loop gain is larger than our open loop gain, in this case by a factor of 1,000, because AOL times K is a number that is less than 1, okay? If instead AOL were 9.9, so this is literally just I think it's a 1%, yeah, 1% decrease in our open loop gain. If we leave our feedback network alone, so 0.999, our closed loop gain in this case is going to be 9.9 divided by 1 minus 9.9 times 0.0999. throw that into your calculator and please tell me what you get. 900.819, I believe. Okay. So essentially, what we see here is that a 1% decrease in open loop gain caused a 90.992% decrease in the closed loop gain. Okay. Well, why might this gain sensitivity be impactful for op-amp circuits? I talked about this a little bit a couple of class meetings ago, but the open loop gain values that we get for an op-amp are a typical value over a production run. But from individual unit to individual unit, we can see a large variation in the open loop gain, which means in a positive feedback system, we're going to see a large variation in the closed loop gain as well. Okay. So it's still going to provide amplification, but it's not going to provide necessarily a consistent amount of amplification, which means we need to use these positive feedback networks for applications where we don't need the gain to be consistent. We want things to either be VCC plus or VCC minus. If we're trying to have any control over it, positive feedback is particularly bad. Now, let's talk about what would happen if our feedback factor in this case were 0.1 instead of 0.0999. What would our denominator be? 0. So our closed loop gain would effectively be our open loop gain divided by 0, which we could consider to be an infinite amount of closed loop gain. Well, what does an infinite amount of closed loop gain mean? Essentially, it means we can potentially generate an output signal for no input signal. In a lot of applications, that is a very bad thing. However, that is actually exactly how electronic oscillators work. So we're going to talk about what's called an astable multivibrator circuit at the end of this class meeting. That's the last circuit that we're going to look at. And it effectively has no input signal whatsoever, but we will see that depending on the values of the capacitors and the resistors that we use to bias our op-amp network, we can generate clock signals. So we will generate square wave oscillations that we can use to control the timing of things. And it's the timing of how quickly it oscillates between VCC plus and VCC minus is dependent on the components that we choose to connect to that positive feedback op-amp network. All right, so I think this is enough background information for now. So let's actually talk about the circuits. So I'm going to pull up LT Spice real quick. And I've already built a circuit for us to look at. So here we go, noisy comparator and Schmidt trigger. So this circuit here in the middle of the screen is essentially the comparator that we built at the end of our last class meeting, right? So when I simulate this guy, and over here for my input signal, I have my simple sinusoidal input, and then on top of that, I have some noise like we talked about. So if I plot my input signal here, and then my output signal here, we see that we have that issue with ringing that we talked about at the end of the last class meeting. So whenever we have a noisy input, our comparator tends to freak out around the reference voltage. Over on the right-hand side, I have a positive feedback op-amp circuit that is more commonly known as the non-inverting Schmidt trigger. And so if I plot the output signal of this guy, we can see that we get the nice consistent square wave that we would expect without any of that ringing. But where we transition from VCC minus up to VCC plus, and where we transition from VCC plus down to VCC minus has changed. And the values of those voltages are going to be dependent on the size of those resistors in our feedback network, okay? So I want us to do a little bit of math and circuit analysis and see if we can figure out the relationship between what the values of those resistors are and where those transition points are going to happen. Okay. So the first circuit that we're going to look at is what's called the non-inverting Schmidt trigger. It's exactly the one that I had implemented in LT Spice. Okay. And I'll draw it here for you guys. So we've got our op amp here. I'm going to choose to put the non-inverting input terminal on top, the inverting input terminal on bottom. And my output signal is going to be over here. So this circuit utilizes positive feedback, as we've been talking about. And so how I'm going to implement positive feedback with an op amp is I am just going to give myself a feedback path or a conductive path from my non-inverting input terminal to my output terminal, okay? So I now have feedback, okay? And in this case, positive feedback because I'm connecting, I'm taking my output signal and I'm sending a portion of it to that positive terminal. So that's what's telling me it's positive feedback. I'm going to call this resistor R2. And then between my input signal and that non-inverting input terminal, I'm going to replace a resistor R1 like so. Okay. On my inverting input terminal, I'm going to apply my reference voltage, much like I had with my comparator circuits. Okay. So in order for us to analyze this guy and kind of figure out what's going on, we're going to need to use that practical op-amp model that we introduced a couple of class meetings ago, right? So my practical op-amp model representation of this guy, I'm going to start with just the op-amp model itself. So here's my input resistance, Rn. I'm going to say that this terminal up here is my non-inverting input node. This terminal down here is my inverting input node. And so that makes this my differential voltage, VD. Over here to the right, I'm going to put in my output side of things. So here is my dependent source, which has a gain of AVOL times my differential voltage, VD. Here's my op-amp's output resistance. And now I have my simple ground bus down here. Okay. So are we all okay that this is indeed our practical op-amp model? Okay. So if I look at my circuit above, I know that I have a reference voltage connected between the inverting input terminal and ground. So I'm going to put a voltage source here representing my reference voltage Vref. Between my non-inverting input terminal and ground, I'm going to have that resistor R1 in series with my input voltage. So here's R1. Here is my input voltage. And the last thing I need to do is to apply my feedback network, which is just my resistor R2. So R2 is going to be connected between my non-inverting input terminal and my output terminal. So here is my feedback network. It's going to be feedback resistor R2, like so. And then my output voltage is going to be the voltage measured between here and here. So before we start analyzing this guy, does anybody have any questions or comments about how I redrew that circuit? Nikolai, how may I help you?
Next to our voltage, our VD, that resistor, is that R, I, what?
Rn.
R?
Yeah. So recall that for the practical op-amp model, it's characterized by three different quantities: our open loop voltage gain, AVOL, our input resistance, Rn, and our output resistance, Rout. And then everything that's connected to that network are the external biasing things for the op-amp itself. Okay. Just for what it's worth, because I didn't actually write these on here, I'm going to make a note. Here's VCC plus, and here is VCC minus, which are our constraints for the maximum possible output voltage and the most negative output voltage as well. Okay, so we could analyze this circuit as is if we were so inclined. But I'm going to make a couple of assumptions here that are going to make it a little bit easier, make the math a bit less of a pain in the ass. Okay. So the first assumption that I am going to make is that my input resistance of my op-amp, Rn, is much greater than the values of my biasing resistors, R1 and R2. So we talked about this in Monday's class meeting, but whenever I have this particular case, effectively what that's going to do is make sure that the current that's flowing in through the input resistance, let's call this I plus, will be effectively 0 amps. It's not going to be exactly 0 amps, but it is going to be an incredibly small amount of current, usually on the order of nanoamperes or picoamperes. So 10 to the minus 9 or 10 to the minus 12 amps, okay? So it's not truly 0, but it's pretty damn close for all of our intents and purposes. The other assumption that I'm going to make, and this one isn't nearly as important because we don't have a load resistance connected or anything like that, but I'm going to say that R out is going to be much, much less than R1 and R2. So essentially what I am saying here with these two assumptions is that we're going to use kilo-ohm size resistors for R1 and R2 because they are in that sweet spot where they are significantly smaller than Rn, but significantly larger than Rout. So we are biasing this thing, quote unquote, correctly. All right, so if that current I plus is 0 amps, then what is VD going to be? approximately 0 volts. I'm not going to put exactly 0 volts, but it's going to be approximately 0 volts. Okay. So the reason why I'm not putting exactly 0 volts is because if VD were exactly 0 volts, then AVOL times VD would be exactly 0 volts, and our output voltage would be exactly 0 volts, but that's not true. VD is going to be something incredibly small, but AVOL is a voltage that is a gain that is incredibly large. So I should still expect my output voltage to actually be either VCC plus or VCC minus, because again, this is a positive feedback system. So those are pretty much my only options for my output voltage, okay? So let's think about things here really quickly, okay? So if V reference is my voltage at this node right here, and I have essentially no voltage drop across that input resistance, then that same V reference is actually going to be applied, or it's what I'm going to see at the non-inverting input terminal of my amplifier system, right? So I got that by just doing essentially Kirchhoff's voltage law. So if VD is incredibly small and V reference is like 2 or 3 volts, then V plus is going to look like that V reference value plus or minus a nanovolt or two, which isn't enough to actually bother about. Okay. So let's now apply Kirchhoff's current law at our non-inverting input node, okay? So I'm essentially going to be adding this current together plus this current together, okay? So KCL at my non-inverting input node is going to give me the following relationship, okay? So I'm going to have Vref minus Vn over R1 plus Vref minus V out over R2 is equal to 0. Everybody okay with that application of Kirchhoff's current law, where again, we're working with the assumption that the current that's flowing through the input resistance is so small in comparison to the current that's flowing through those smaller resistors that we can effectively neglect it, okay? So what I'm going to do now is I'm going to rearrange this expression, and I'm going to put Vref on one side of the equation, and then V in and V out on the other side of the equation, okay? So I'm going to have, yes.
So in that case, you say we're basically neglecting the input resistance? Is that what's happening?
So we're not neglecting the input resistance itself. We are neglecting that current that's flowing through the input resistance, because since the input resistance is so much larger than R1 and R2, we know that practically no current should branch off and flow through that particular path. Okay. So we're going to have Vref over R1 plus Vref over R2 will be equal to V in over R1 plus V out over R2. I'm going to take that factor of VREF out. So that's going to give me VREF times 1 over R1 plus 1 over R2. That'll be equal to Vn over R1 plus V out over R2. And now I'm going to divide both sides through by 1 over R1 plus 1 over R2. Okay. So that's going to give me the relationship Vref is equal to, I'm going to write it like this, Vn over R1 divided by 1 over R1 plus 1 over R2 plus V out divided by R2 divided by 1 over R1 plus 1 over R2. So essentially here, I've got a common factor of 1 over R1 plus 1 over R2. What is that? Mathematically. Parallel resistance, R1 in parallel with R2. So I'm going to replace that 1 over R1 plus 1 over R2 with just R1 times R2 over R1 plus R2. So if I have Vn times R1 times R2 over R1 plus R2, and that's all divided by R1, the R1s in the numerator are going to cancel out. And that's going to leave me with Vn multiplied by R2 over R1 plus R2. And pretty similarly, I'm going to have V out multiplied by R1 over R1 plus R2. So this is my characteristic equation for my Schmidt trigger. So I know that this looks weird, so this is equal to VREF. Let me box in that VREF over here as well. Okay. So usually, when we've analyzed op-amp circuits and things like that in the past, we've always been interested in finding what our output voltage is. Because we've got a positive feedback system, we know our output voltage is either going to be VCC plus or VCC minus. So what we're really interested in figuring out here is what value of input voltage makes our output change or transition between those two possible outputs, okay? So we're going to call those voltages the upper trigger limit, which is, let me make a note here. So VUTL is our upper trigger limit voltage. Which causes V out to change from VCC minus to VCC plus. And then the LTL is going to be our lower trigger limit voltage. Which causes V out to change from VCC plus to VCC minus. So the upper trigger limit is the voltage is the transition point that makes the output go high, and the lower trigger limit voltage is the input voltage that causes the output to swing low. Okay. So we're going to use that characteristic equation to figure out what these upper trigger limit and lower trigger limit voltages are. Okay. So let's start with the upper trigger limit. Okay. So determining VUTL, okay? So first, we have to assume that V out is equal to VCC minus, okay? So this is where our output voltage is starting at, and we're trying to see what's going to cause it to switch over to VCC plus. So if we put this into our equation, we'll have Vref is equal to Vn times R2 over R1 plus R2 plus V out, which in this case is VCC minus. Let me move that down. Times R1 over R1 plus R2. Well, what we're looking for is the input voltage that's causing this to happen. So I'm going to replace Vn with VUTL. Okay. And now I'm just going to rearrange this guy, right? So we would have essentially VUTL times R2 over R1 plus R2 is equal to V reference minus VCC minus times R1 over R1 plus R2, and then I'm going to multiply it both sides through by R1 plus R2 over R2, and that's going to give us VUTL is equal to Vref times R1 plus R2 over R2 minus VCC minus multiplied by R1 over R2. Okay. So let me switch back over to the LT Spice simulation really quickly. Okay. So if I were to look at this graph, it seems to me like our upper trigger limit voltage is going to be somewhere in the ballpark of 7 volts based on what I'm seeing here, right? So my output is low until my input signal gets somewhere between 6 and 8, and then it swings high. In this particular case, my resistance R2 is 10 kiloohms, and my resistance R1 is 3 kiloohms. VCC plus is 10 volts, and VCC minus is negative 10 volts. So let's see what value we calculate here. So that would be VUTL is going to be our reference voltage, which was 3 volts, times 13 kiloohms over 10 kiloohms, minus VCC minus, which was negative 10 volts, times 3 kiloohms over 10 kiloohms. And if I put this into my calculator, so 3 times 13 over 10 plus 10 times 3 over 10, I get 6.9 volts. Okay. So that seems reasonable. We'll look at it more exactly here in a moment. Okay. If we wanted to determine our lower trigger limit, we would start with an assumption that V out is equal to VCC plus, because we're trying to figure out which voltage causes it to swing down to VCC minus. And so I'd use my characteristic equation. In this case, I would have Vref is equal to V lower trigger limit times R2 over R1 plus R2 plus VCC plus times R1 over R1 plus R2. And I'm just going to rearrange this guy, right? So VLTL times R2 over R1 plus R2 will be equal to Vref minus VCC plus R1 over R1 plus R2. Multiplying both sides by R1 plus R2 over R2 gives me VLTL is equal to Vref times R1 plus R2 over R2 minus VCC plus times R1 over R2. And just for the sake of argument here, let's calculate this. VLTL, sorry, would then be 3 volts times 13 kiloohms over 10 kiloohms minus positive 10 volts times 3 kiloohms over 10 kiloohms. So that's 3 times 13 over 10 minus 10 times 3 over 10. And I get 9/10 of a volt, or 0.9 volts. Okay. So let's take a moment here and look at our simulation. So it looks like my output voltage is triggering low around here. So I'm just coming back over. So somewhere between 0 and 2 volts. So this seems reasonable. Now, there's a better way for us to look at this thing, okay? What I'm going to do is I'm going to delete my input signal. I'm going to delete my comparator's output signal, and I'm going to plot the output of my Schmidt trigger circuit. Instead of as a function of time, I'm going to plot it as a function of Vn plus N. And let's see what happens here. So I can see that it's telling me my X value. Look in the bottom left-hand corner of the screen here. It says that my X value for this transition, where it's going from low to high, says 6.82 volts. So not exactly 9 volt or 6.9 volts, but pretty darn close. And pretty similarly over here, my lower trigger limit voltage, it has it at X is equal to 0.89 volts, which is pretty darn close to 0.9. So this is doing a pretty darn good job of approximating what those upper and lower trigger limit voltages are, despite the fact that we've made some assumptions about how this thing behaves, okay? For what it's worth, I want to show you guys essentially how to read this graph, because this is exhibiting what we would commonly call hysteresis in our signal. So essentially what we've got is our input signal is starting at negative 10 volts, and then it's gradually increasing, okay? Keeping on going, keeping on, keeping on, keeping on, keeping on, until we hit our upper trigger limit. Then it's swinging high. and then it's gonna saturate at VCC plus until we hit positive 10 volts, and then we're gonna back off that voltage. So it's gonna stay here at VCC plus until we lower the voltage enough so that we go lower than V lower trigger limit, and then it switches back down to 0. So the way that this is going is from left to right along the bottom, jumping up, continuing to the right, then going from right to left on top until we hit our lower trigger limit, jumping down to the bottom, and then continuing to the left. Yes, Josh?
Is there a reason why it jumps like that, when it hits, when it jumps up, when it jumps high, like kind of a slight increase into the major?
I think that
Or is
that's
that
really
like
just an artifact of the noise and all of that kind of stuff, like it should effectively just be a box. So I think that that's just a little hiccup in the simulation, nothing particularly wild or crazy there. Okay, we've got 5 minutes left. So I'm not gonna be able to talk about the multi-stable, or excuse me, the astable multi-vibrator circuit today, but we can talk about an inverting Schmidt trigger really quickly, okay? So my inverting Schmidt trigger circuit my stylus is being dumb. Is essentially the exact same thing as my non-inverting Schmidt trigger circuit, except that I'm going to swap Vref and Vin, exactly like I did between going from a non-inverting comparator to an inverting comparator. So my circuit should look something like this. Here's my non-inverting input terminal. Here's my inverting input terminal. I should have positive feedback, where that feedback resistor's value is going to be R2 again. Here's V out. Between my reference signal here, Vref, and my non-inverting input pin, I'm going to have the resistor R1. And then down here, I'm going to apply my input signal directly to my inverting input pin. And just for what it's worth, here's VCC plus, and here is VCC minus. So I'm not going to bother drawing the full-on practical op-amp model representation of this circuit because it's really unnecessary. When you guys are finished copying this down, I'm going to scroll up really quickly, and we're just going to talk our way through it. All right, so this circuit right here is my schematic diagram or my practical op-amp representation of the non-inverting Schmidt trigger. So what would the only change that we would need to make this an inverting Schmidt trigger? What would that change be? Swapping Vref and Vn. So instead of literally rederiving all of this stuff because it's completely and utterly pointless, if I look at my equation and I swap Vref and Vn, that's going to be the result of that analysis, right? So what we will have for our characteristic equation is actually just Vn will be equal to Vref times R2 over R1 plus R2 plus V out multiplied by R1 over R1 plus R2. This is incredibly convenient for us because for the inverting Schmidt trigger circuit, we literally don't have to do any algebra whatsoever to calculate our upper trigger limit voltage or our lower trigger limit voltage, right? So our upper trigger limit voltage, so that's the voltage that's going to cause our output to change from VCC minus to VCC plus still, is literally just going to be Vref times R2 over R1 plus R2 plus VCC minus times R1 over R1 plus R2. And similarly, our lower trigger limit voltage is going to be Vref times R2 over R1 plus R2 plus VCC plus times R1 over R1 plus R2. All right, so that is enough out of me for today. We'll kick things off on Friday's class meeting with that astable multi-vibrator circuit. I'll go ahead and build it in LT Spice so that we can just jump into talking about it right from the jump. And then we'll get into negative feedback circuits and the properties of negative feedback after we finish up that oscillator. All right, thank you guys for your attention. I will see you on Friday.